Hello everybody and welcome to Lecture 1 in the Introduction to Electromagnetism series here in this channel. This will be a series of lectures going over everything in electromagnetism at an early university level, everything from electrostatics to electrodynamics, Maxwell's equations, and their applications. This Lecture 1 will be covering electric charge and Coulomb's law. So let's begin. Electric charge is a fundamental physical property of subatomic particles. It comes in two different types, positive and negative charge. Positive charge is associated with the subatomic particle, the proton, and negative charge is associated with the electron. Now there is a third subatomic particle that is the building block of all atoms and matter. That will be the neutron, but the neutron, as the name suggests, is neutral, so it has no electric charge, and therefore we don't really work with it at all. The unit of electric charge is the Coulomb, typically just written as C. The proton has a charge of about 1.6 times 10 to the negative 19 coulombs. The electron has the exact opposite charge, negative 1.6 times 10 to the negative 19 coulombs. And then the neutron, being neutral, has a charge of 0 coulombs. Now, electric charge has two important properties. First, electric charge is conserved. It may never be created or destroyed. And what do we mean by this? Say we have some distribution of charge. Here we have 4 positive charges and 2 negative charges. Our total charge within this circle is plus 2 positive charges. Now, say that something happens within the problem. Maybe 2 of these charges combine. Maybe they're electrons and protons and they create a hydrogen atom. So now we went from having a distribution of 4 positive charges and 2 negative charges to now having 2 neutral particles and 2 positive charges. Now if we ask what is the total charge within this same problem, it's still positive 2. We have 2 neutral particles now and 2 positive charges, and that gives a charge of plus 2. What do we learn? Well, even though things happened within this circle, within this problem, the total charge did not change, and it will never change in a closed problem. What do we mean by a closed problem? Well, as long as we never take a positive charge or a negative charge out of this circle or introduce a new charge within this circle, the total charge is always going to stay the same. No matter what happens within this circle, the total charge will always remain plus 2. The second important property of electric charge is that electric charge is quantized. So in nature, electrons and protons are the building blocks of everything that has electric charge. Everything is made out of electrons and protons, and therefore the charge of anything that's made out of electrons and protons will have a charge that is some multiple of the proton and electron charge. So mathematically, this is the charge of any atom is going to be equal to n, where n is some integer, times the charge of the proton, 1.6 times 10 to the negative 19 coulombs. The integer n is simply given by the number of protons minus the number of electrons. So for example, what is the charge of an ionized carbon atom? So carbon has 6 protons. When it is fully ionized, it has no electrons, and thus the charge is equal to 6 times the proton charge, 1.6 times 10 to the negative 19 coulombs, and that gives a total charge of 9.6 times 10 to the negative 19 coulombs. All right, now moving on to Coulomb's law. So in addition to these two important properties associated with charge, electric charges also experience a force due to other electric charges, and this is known as the Coulomb force. So as you may have known from the common saying, opposites attract. If you have a positive and negative charge near each other, they will be attracted to each other, so the force will be attractive. However, like charges repel. So if you have 2 negative charges, they will move away from each other, and same with 2 positive charges, they will repel and move away from each other. The magnitude of this electric force is given by what is known as Coulomb's law. So if we have 2 charges, Q1 and Q2, separated by some distance r, the magnitude of the force between these 2 charges is given by the equation 1 over 4 pi epsilon naught times the absolute value of Q1 times Q2 divided by r squared. Now, there's a number of interesting things to point out about this equation. First is that you may not be familiar with the constant epsilon naught. This is known as the vacuum permittivity. It is simply a constant that comes up a lot in electrostatics and electrodynamics, and it has the value of 8.854 times 10 to the negative 12 farads per meter. You also notice that this force has a 1 over r squared dependence, and this is just like gravity. So it makes this equation a little bit easier to remember. Just like gravity, the force has a 1 over r squared dependence. And then finally, you notice that the force is proportional to the magnitude of the charges on both particles. So F is proportional to Q1 times Q2. In this case, we're taking the absolute value of these charges because right now we're not concerned with the direction, just the magnitude of the force. This equation may also be written as F is equal to K times the absolute value of Q1, Q2 divided by R squared. This is the exact same equation. It's just a good example of physicists being lazy and not wanting to write. In this case, K is equal to the constant 1 over 4 pi epsilon naught. This is something that you may see in problems or in books. But what direction does the force point? So this equation only gives the magnitude of the force, but this force also has a direction associated with it. It is a vector, and we can modify our equation slightly. It becomes a little bit more complicated since now it becomes an equation with vectors, but it is given by this equation right here. So the vector F12 is equal to 1 over 4 pi epsilon naught Q1 times Q2 divided by R squared times the unit vector R12. So what do each of these vectors mean? It can be a little bit confusing with the notation, but we'll break it down. So F12, how you read this, F12 is you read this as the force by Q1 on Q2. So we have two particles, Q1 and Q2. The force by Q1 onto Q2 is given by the vector F12. Then R12 is the unit vector, so it has a magnitude equal to 1, pointing from Q1 to Q2. So R12, the unit vector, is given here in this problem, pointing from Q1 to Q2, and is given by the unit vector R12. So let's try an example. We can switch things up a little bit. What is the force by Q2 on Q1? So it's similar to the first case that we just went over, but in this case, we're looking at the force by Q2 on Q1 instead of by Q1 on Q2. So maybe a little bit confusing. So now we have F, which is read F by Q2 on Q1, the vector, is going to be equal to 1 over 4 pi epsilon naught Q1 times Q2 divided by R squared times the unit vector pointing from Q2 to Q1. So it's always very helpful to actually draw the vectors on the problem. So if we draw the unit vector R21, this will be pointing from Q2 to Q1, like so. And then we're looking at the equation, we suspect that F points in the same direction. So the force by Q2 on Q1 points away from Q2. However, if we do a quick mental check and say, okay, we have two opposite charges, we know that opposites attract, F21 should be pointing towards Q2 if it was an attractive force, but clearly we have it pointing away. So somewhere we messed up. Well, where did we mess up? We messed up in that we forgot to remember that Q2 is negative and no longer is in an absolute value sign when we care about the direction. So if you only care about the magnitude of the force, you don't care about the signs of the charges. However, when you start caring about the direction of the force, you need to take into account the signs of the charges. So Q2 here in this equation will be a negative value, and a negative vector will flip the direction of the vector 180 degrees. So instead, it could be maybe written more clearly like so. So F21 is equal to negative 1 divided by 4 pi epsilon naught, the absolute value of Q1 times Q2 divided by R squared, and then the unit vector R21. So if we want to draw the vector correctly, now that we remember to take into account the negative sign, it would instead look something like this. Now we are correct in our thinking that opposites attract, and we have the correct direction of the force. So we can do an example problem. So question, a neutral carbon atom is 3 meters away from a particle with charge 5c. What is the force on the neutral carbon atom due to the other particle? So a little bit of a trick question, but there is no force. So neutral particles do not experience the Coulomb force. Essentially, this can be seen quite easily looking at the Coulomb law, just looking at the magnitude of the force. F is equal to 1 over 4 pi epsilon naught, Q1 times Q2 divided by R squared. For a neutral particle, Q is equal to 0. So F is going to be equal to something multiplied by 0, and thus F is equal to 0. We can do another example problem. So question, two particles are 4 meters away from each other. One with charge Q1 is equal to 3 coulombs, and the other with charge Q2 is equal to 6 coulombs. Find the magnitude of the force on each particle due to the other, and draw the force vectors. So if we draw this scenario, we have two positively charged particles, one with Q1 is equal to 3 coulombs, the other with Q2 is equal to 6 coulombs, and these two particles are 4 meters apart. We can start by calculating the force by 1 on 2, so this would be F12. We can first draw the unit vector R12. So this is going to be the unit vector pointing from Q1 to Q2. And then we know from our Coulomb's law that this F12 is given by the equation 1 over 4 pi epsilon naught Q1 Q2 divided by R squared. And then the unit vector R12. So if we plug in the values here, we have 1 over 4 pi epsilon naught, 6, the charge of Q2 times 3, the charge of Q1 divided by the distance in between the charges, squared, so 4 squared, and then the unit vector R12. If we plug in the numbers, we get a value of 1.01 times 10 to the 10 newtons, and then we know that everything here is positive, so F12 is going to be pointing the same direction as R12, so we can draw F12 right on Q2. We can then repeat the same process, looking at the force by Q2 onto Q1. However, we can go through this whole same process, but if we think a little bit, you know possibly from previous courses that every force has an equal and opposite reaction, or otherwise it may just be quite intuitive to you to see that F21 is just going to be the same magnitude as F12, just pointing in the opposite direction. So we know that like charges repel, so F12 is going to be pointing away from charge Q1, and then F21 is going to be pointing away from charge Q2. So it'll be a vector of the exact same magnitude as F12, just pointing in the exact opposite direction. Now this concludes the first lecture in our Introduction to Electromagnetism series. The next lecture will be going over superposition and electric fields. I hope you learned something this lecture. If you did, please like, and if you enjoyed the video, please subscribe. Thanks.